Iterators versus standard loops. Should you use a basic loop to print each password character, or leverage an iterator combined with the next method? Why choose an iterator? Let's break it down. Here's exactly how it works. Look at this password string. We want to stream these characters one by one. We initialize an iterator. This object tracks your exact position across the sequence, managing the data stream smoothly. Every time we call the next method, it fetches one character. Running this code yields the first two elements, A and 1. This is our iterator. Now, we have a fully functional iterator object. It acts as a standalone object. Invoking next instantly retrieves the upcoming character. So why not just use a standard for loop here? As you can see, a loop prints every single character instantly. Since strings are iterable, looping is completely seamless. But here is the real magic. With an iterator, you gain total control over when the next character appears. You direct the execution flow. That is key. With a standard loop, you lose that fine-grained power. Once a loop begins, you simply cannot pause it. With iterators, we can pause at will, then resume whenever you want. Call next again, and the letter appears. We can repeat this at will, step by step, pulling exactly what we need when we need it. Standard loops lock you into a rigid path, all at once. While workarounds exist, this control is why iterators shine. Use next for absolute precision and targeted consumption. You simply cannot pause a loop. With iterators, we pause and decide the next move. Let's call next once more. This fetches the very next character in the sequence. We can repeat this loop as needed. Item by item, there is the next character. Compare that to a loop, which locks you into a routine. It is forced to process every single character at once. While workarounds exist, this control is why iterators win. Use next for precision and targeted data consumption. It allows you to pause, resume, and process streams incrementally. That is the ultimate power of using the next method. That is when you want to use next. While a standard loop simply dumps the entire dataset at once. Check out this incredibly powerful use for an iterator. We are going to strip out the header row completely. Imagine your raw data arrives formatted exactly like this list. Whether you are reading from a flat file or pulling live records straight from a database, notice that the very top row is our header, name, email, and department. Our goal is to cleanly isolate that header before we start processing the rest of the data. This is a brilliantly elegant use case for an iterator. It focuses on mastering iterators over basic workflow. It is fascinating. Look closely here. Since we are working with a list, we can easily generate an iterator. This lets us step through the items seamlessly. Remember, this main list contains nested lists. We want to process each nested item sequentially as we move forward. Notice right here, we are invoking the next function. It may seem a bit detached, all on its own, but it is actually a built-in global function available everywhere in Python. We pass our iterator right into it. The sole job of the iterator is to fetch the very next row on command. Remember when it is first initialized? It points right before the first data row, but the moment you trigger the next function, it grabs the first item, which is the header. Once we grab that header row, we immediately capture and store it in a variable. We print it. Right after that, we will print a clean separator line underneath it. See how clean that looks? This divider is created by a swift piece of code, multiplying a single dash by 35 times. This gives us exactly 35 dashes. This is an incredibly common Python pro tip. Next, we are going to loop smoothly through every remaining row via the iterator. Pay close attention here. We are executing the loop directly on the iterator itself, not on the original raw data list. Notice that the original list variable stops right here. Now, we loop exclusively through the iterator. Python will automatically call the next function for us, seamlessly printing out every single row one by one. This gives you complete, absolute manual control over exactly where you extract the header and insert your visual divider. No loop is needed for the header. The loop only begins down here. Can you see the immense power of an iterator now? You gain precise control over your entire program's execution flow, letting you run complex logic well before you ever touch the core data processing loop. This is a great way to start shifting your mindset toward what is truly possible with iterators. And just like that, the individual rows print out flawlessly. Master this pattern, and you will elevate your real-world data processing scripts completely. Pure coding magic? Let's master the game-changing concept of custom iterators. Standard iterators loop through existing items, but here we build our own custom logic. We are designing a completely unique Python class called ticket numbers. This class automatically issues unique IDs Whenever your code requests a ticket, it instantly delivers the next one available. To implement this, we write special double underscore methods. In Python, these are known as dunder methods. First, we define the dunder iter method. We place 2 underscores on each side. That is exactly how they look. Now we add a parameter. The standard choice here is to name it self. Think of self as object memory. It tracks state. Inside, we initialize a variable representing our tracking number. We will start this count at exactly 100, then return self. This object serves as our data store. Everything is saved. Next, we create the dunder next method. Its job is to fetch the current value. It references that object memory. We access the number variable we just set up and save it locally to return. Right after that, we modify the original state. We increment the stored count by 1. This prepares the next value perfectly. Let's increase it sequentially. Now, let's observe how the values behave. See this? It runs seamlessly. Awesome. Let's instantiate our custom class now. Look, everything is set up properly. We initialized it. We will store this instance in our object variable. So look, now we can cleanly extract values from it. We trigger the sequence by executing the next function. This calls our custom method under the hood. Watch what happens when we execute this. We get 100, 101, and 102. The outputs generate perfectly every single time. And that is how you build a powerful custom iterator in Python. How do you stop a Python iterator from looping forever? Let's look at this custom countdown iterator example. We are creating a countdown class, starting our counter at 5. Notice these special double underscore methods right here. These are known as dunder methods. They are standard methods that Python expects. Whenever you create an iterator, or when a for loop automatically builds one on your behalf, you are telling Python exactly how to loop through this class. The exact mechanics of how this loop executes are fully defined right inside your class code. So we must implement the exact methods that Python is looking for. You cannot just name them anything you want. Naming it something like Iterator2 simply will not work. It will throw an error stating that the object is not iterable. That is why it must have the dunder iter method spelled exactly like this. The method signature and name must match perfectly. Now, this self variable points directly to the specific instance of our countdown object. The moment you instantiate this class and create an object, Python sets everything up. It will track that unique instance perfectly. We will initialize it with a starting value of 5. Inside, we create a variable named number and set it to 5. As the loop executes, it triggers the dunder next method on every single turn. Python explicitly expects the word next. You cannot deviate from this. Naming it next2 will fail instantly. It simply will not return the correct iterator type that Python is looking for. So you must name it exactly next, just like this. Now, let's see what happens when it runs. It grabs the current number, which starts at 5, and prepares to return that value to the loop. Crucially, it also decrements the number by 1. This reduction happens seamlessly on every single pass, giving you a perfect countdown: 5, 4, 3, 2, 1. Next, we introduce an if condition right here. Once the number hits 0, we want to raise a stop iteration exception. Watch what happens when we run this code now. We get a clean printout from 5 down to 1. Yes, to include 0 in the output, simply change the threshold to -1. And just like that, it counts all the way down to 0. You can see how incredibly powerful this is. But what happens if we omit this condition? Let's revert this back to 0 and find out if we completely comment out this stop condition. Without raising stop iteration, our code will run forever. Look at it go. It just keeps running endlessly, plunging deep into negative numbers. Let's halt this execution right now. Raising the stop iteration error is essential because the for loop catches it and terminates the counter safely. This is a built-in standard exception you must raise. Again, you cannot invent a custom name like stop iteration error 2, as that will completely fail. Right, it is simply not valid. Ever wonder how to create a Python module? Let's dive straight into the code. We've got our main.py file ready. Right now, all of our code is crammed into this single file. We have calculate revenue and hire sale functions, along with the core application logic, all sitting together in one place. But clean code means splitting this up. Those calculation functions belong elsewhere. Let's build a Python module. We'll create a dedicated analytics module to import and reuse these functions anywhere. Running the code right now works perfectly fine because calculate revenue uses the sum method to process all incoming monthly sales to find the total revenue. Meanwhile, hire sale grabs the maximum value, which is 2,100, with a sum of 6,050. Let's cleanly modularize this. To keep our project professional and organized, first, let's create a brand new file. We'll name this file analytics, and just like that, analytics.py is live. Right now, it's completely blank. So let's shift those two functions over. We will simply cut them from here. Right-click to extract them and paste them right into analytics. Perfect! Now our analytics file houses both functions back in our main file. Notice something? We get errors because they're not defined yet. Time to unleash the import statement. Let's type import analytics as an. By aliasing the module as an, we can easily call its functions here. And look at that, our module is successfully imported. The functions are ready to roll. Let's run the code again and check out the flawless output right here. We now have a beautifully split architecture. Analytics handles all the heavy lifting behind the scenes, while our main script cleanly imports and executes them. And that's how you build a Python module. Want to master Python modules? Let's build and import functions. Right now, our project only contains a single main.py file. Just one file. Keeping all your code in one place is a major bad practice. To write professional code, we need to clean this up. If we execute this script, you will see a simple list of numbers, where we calculate the sum and identify the highest sale value by passing the variable into a max function. Right here, these functions are very basic. They really belong in their own dedicated file. Let's head over to the sidebar. Inside VS Code, I will click on the new file icon. Let's click it. We will name it Analytics and append the .py extension. This tells Python it's a code module. Now let's jump back to our main script. We will migrate these two functions out. Simply highlight, right-click, and cut them. Next, paste them right into our new analytics file. Perfect. They live here now. Back in main, Python throws an error because it can't find them. To fix this, we need to import these functions directly. We will start with the keyword from, then target our module name, type analytics. Look how IntelliSense automatically finds it, right inside our project directory. Now, let's pull it in. Next, we will explicitly bring over our two functions. Just use the import keyword followed by their names. As we type, autocomplete suggests calculate revenue. Let's select it and add a comma for the next one. Notice how the first error instantly vanishes. The IDE recognizes it immediately. Now, watch the remaining error under highest sale disappear as soon as we append it to our import statement. Once imported, the warning line completely clears up. Let's run the code and check the terminal. Boom, we get 650 and 2100. So what did we just achieve? We isolated our logic into a clean separate file named analytics.py. Then we integrated that module straight back into main. We leveraged the from keyword to target the file and pulled the specific functions using import. Now everything is modular and it works flawlessly. That is how you build production-ready modular Python code. Keep your files clean and your functions organized. If you leveled up your skills today, smash that like button, drop a comment, and subscribe. Stay tuned for more clean code tutorials. See you next time. In Python, you can actually store functions inside variables. Take a look at these two functions, calculate revenue and highest sale. Watch closely right here. We are assigning these functions directly to a variable named calculation. This unlocks incredible dynamic power. Imagine a front-end user who selects maximum as their report type. When that happens, our code triggers the else clause and routes the calculation to the highest sale function. But if they choose revenue, it seamlessly switches to execute the revenue function, defined right here. Let's see this in action. On the screen, we have both functions defined at the top. Standard setup. Next, a variable captures the user's specific choice, followed by our monthly sales data, which is a simple list of numbers. Now, we pass that list into the correct function, driven entirely by the user's selection. Since the user selected maximum, it doesn't match revenue. This triggers our else block. The calculation variable now dynamically holds the highest sale function. It's storing a direct reference, not running or executing the function just yet. It simply points to that function. Then we invoke the calculation variable, passing our monthly sales data straight into it. Let's run the code and print the result. Boom, we get an output of 2100 that perfectly matches our maximum sale value. The correct code executed flawlessly. Python handled it beautifully. Now, let's test revenue. If we change the user selection to revenue and rerun the script, the result changes to 6,050, while the peak sale remains 2,100. That is how seamlessly you can store functions inside variables. Use this trick to build highly dynamic, scalable applications. Pretty incredible feature of Python, right? It makes clean coding a breeze. While other languages support this, Python keeps it incredibly elegant and simple. If you found this valuable, smash that subscribe button, drop a comment, and leave a like to show some love. See you next time. Ever wondered how to rename functions dynamically in Python? Take a look at calculate revenue and highest sale. Can we safely rename them? Absolutely. The cleanest method is to declare a new variable and directly assign it to your target function. Here, our new revenue variable points straight to the calculate revenue function, while the top sale variable seamlessly references the highest sale function. Under the hood, Python treats functions as first-class objects in memory. Think of it like a direct address to a friend's house, just like how famous global cities have popular nicknames, where Philadelphia is shortened to Philly, or New York is smoothly abbreviated to NY. We can apply that exact same shortcut logic directly to our Python functions. Instead of typing out long names like calculate revenue, we can now use sleek terms like revenue or top sale to reference the original code. Now, you can execute these functions instantly by simply calling their brand new variable names. Let's run the code and watch the magic happen in real time. Notice how we append parentheses to pass our monthly sales data straight into the newly aliased variables, returning the exact output we need. It is that simple. Even though it looks like a standard variable, hovering over it reveals it still tracks back to the revenue function. Using the original name gives you standard syntax highlighting, making it visually obvious that it's an active function. With aliases, highlighting changes. But why would you want to do this? Imagine executing custom code based on dynamic user input. If a user selects dynamic revenue tracking on the front end, you can route their choice through a single unified variable name. Just one variable. Let's create a generic variable called calc. Both paths will use calc. Now, whenever calc is invoked in the script, it automatically executes the user's specific choice, dynamic and efficient. Wrap it in a simple if statement to verify what the user selected. If they request revenue data, then the revenue logic fires. Setting this up takes just a few lines of code. It looks exactly like this. Check the input. If the input equals revenue, execute the revenue track. Otherwise, trigger the fallback option. Python handles the rest seamlessly, bringing everything back to our core concept. You can completely rename Python functions using variables. Can you store functions inside a Python dictionary? Let's look at these two functions, calculate revenue and highest sale. They handle standard math operations, specifically a sum and a maximum. When we execute this script, we instantly get our results. The outputs return 6050 and 2100. This data array holds the numbers we want to aggregate or maximize. Take a close look at this dictionary right here. Notice the clean syntax with curly braces and colons. We map a distinct key to a powerful value. By targeting the revenue key inside our reports dictionary, we point directly to the underlying function object, passing our monthly sales data to trigger execution. And just like that, we get 60, 50, and 2100. The same logic applies to find the highest sale. The same rule applies when accessing our keys. This key holds our executable function directly, which triggers instantly using standard parentheses. That pair of parentheses is the secret sauce. Watch what happens if we remove those parentheses entirely. We reveal what Python sees under the hood. Let's delete them. Now, when we run this Python file once again, notice how the terminal output changes completely. It prints the function's raw memory address. That is exactly what the revenue key points to natively. But the moment you append those round parentheses back and pass your target variable inside them, it immediately executes the code. Without them, it's just a memory address. With them, you unleash the function's full power. It's an incredibly slick Python feature. Key value pairs, where the values are live functions. If you love mastering clean Python tricks like this, hit follow and subscribe. Drop a comment below to support more high-value coding breakdowns. Let's keep building epic projects together. See you next time.